We are diving deep today into what is probably the unsung hero of engineering analysis, the electronic spreadsheet. We're talking about tools like Microsoft Excel, but specifically how professional engineers really use it, moving past basic data entry and turning it into a genuine computational powerhouse.
It's such a critical topic. Our mission today is to really get into why spreadsheets are just indispensable for modern engineering, from, structural calculations all the way to analyzing experimental data.
And you have to think about the history here. Not that long ago, if you as an engineer had a big problem to solve, a huge system of equations or something, you had two options.
Right.
Spend a week with a massive calculator, or more likely you'd write a custom program. We're talking languages like Fortran.
And if you've ever had the, let's say, pleasure of debugging a few thousand lines of Fortran code, you know exactly why spreadsheets were so revolutionary.
I can't even imagine.
The reality now is that for most problems that involve recording, organizing, and analyzing data, spreadsheets are just more efficient, way easier to use, and this is the big one. So much easier to debug.
And that ease of use means you can iterate faster. You can plug in a physical law, change one variable, and see the result instantly, numerically and visually.
That's the core value. Data, formulas, and charts all in one place. It makes the work so much more accessible.
Okay, so to unlock all that, we need to speak the language. We don't have to spend a ton of time on the absolute basics, but you do need to know where the power tools are.
For sure. So let's just quickly cover the structure. You have the main file, that's your workbook. Inside, you have multiple worksheets.
And the worksheets are your grid, right? The lettered columns and numbered rows. Where they meet, that's a cell.
Exactly. And the concept that becomes immediately useful for any real engineering work is the range.
So that's just a block of cells, like a chunk of your data.
Right. It's defined by the top left cell, a colon, and then the bottom right cell. So something like A3 but B10. That describes a specific matrix of your data points.
And this is where it starts to get powerful, I think. Naming those ranges. You can select that A3 part B10 block and just call it temperature readings.
Yes. And then your formulas become so much clearer. Instead of some obscure cell address, your formula literally says average temperature readings. It's faster, it's clearer, and it prevents a ton of errors down the line.
So it's all about that initial organization.
That structure is what leads us to the engine of all this, the formulas. And the first rule of formulas is
it has to start with an equal sign. If you forget that, you're just typing a word.
you're just typing a label. And the basic math is intuitive. Plus, minus, multiply is the asterisk, divide is the slash, and the caret for raised to the power of. But the real danger isn't the symbols.
It's the order of operations.
It's the silent killer. This is where really costly engineering mistakes can happen.
So give us an example of that.
Okay, say you're calculating a force and you type 100 plus 52. The system is going to do the multiplication first, right? So you get 110.
Right, PEMDAS.
But maybe your physical model needed you to add the 105 first. If you don't use parentheses, so 100 plus 52, you get 210. Your result is off by almost 100%.
And the scary part is Excel isn't wrong. You just haven't told it the right order to do the math in.
Exactly. But once you've got that down, the true secret to automation for engineers is mastering cell referencing.
This is what determines what happens when you copy a formula across hundreds or even thousands of cells.
And there are three types, and you really need all of them. The first one is the one that Steve's put, the absolute reference.
Okay, so that's the one with the dollar signs, like $3.
Right. When you copy a formula with that in it, that reference never changes. It's always pointing back to cell A3. You use this for constants.
Like the acceleration of gravity or a fixed interest rate, something like that.
Exactly. Then you have the default, the one you use most of the time, the relative reference.
Just A3, no dollar signs.
Right. If your formula in cell B3 points to A3 and you drag it down to B4, the reference automatically updates to point to A4. It's essential for processing long columns of data.
But the one that I think is the most powerful and maybe the least understood by new users is the mixed reference.
Oh, absolutely. This is the one that can save you days of work. A mixed reference is selective. You can lock just the column, like $3, or just the row, like A3.
And the real power of this comes in when you're building, say, a big lookup table. The sources give a great example of this.
Yes, the interest calculation table. Imagine you have 50 different principal amounts listed down column A and 50 different interest rates across row 2. You want to calculate the interest for every combination.
That's 2,500 calculations.
But you only have to write one formula. In cell B3, you'd type A3B $2.
Let's break that down, the $3 part.
That means when you copy the formula, it will always look in column A for the principal amount. The A is fixed.
But the 3 is relative, so it will update to 4, 5, 6 as you drag it down.
Correct. And then the B2 part means it will always look in row 2 for the interest rate. The 2 is fixed, but the B will change to C, D, E as you drag it sideways.
And with that one formula, you can fill the entire 50 by 50 grid instantly. That's incredible.
That is the essence of automation right there.
So we know how to write our own logic. Now let's talk about leveraging Excel's own massive library of pre-written logic, the functions.
Right, these are just prepackaged formulas. You can type them out or use the little FetX button to find them. For engineers analyzing data, some are just non-negotiable.
So which ones are the absolute must-haves?
Well, the statistical functions are foundational. Of course, you have SUM, count, max, MIN. But the most critical for evaluating data are average and SDDV for standard deviation.
Okay, so what is the standard deviation telling an engineer that the average doesn't?
Great question. Let's say you're measuring the density of concrete from 2 different suppliers. The average density might be identical for both. It might meet the spec. But the STDEV tells you about the consistency. A high standard deviation means your measurements are all over the place. It suggests a major quality control problem with that supplier, even if the average looks okay.
So it's a measure of reliability, not just the central value.
Exactly. And of course, you have all the built-in math and trig functions, PI, COS, SN, square feet for square root, functions to convert between degrees and radians. It just handles all that overhead for you.
Okay, now let's get into automating decisions, not just calculations. This is where the logical functions come in.
This is where you make your spreadsheet smart. You're using functions like AND or not D, and the most important one of all, the IF function.
The IF function basically lets the spreadsheet make a choice.
It does. It tests a condition. If the condition is true, it does one thing. If the condition is false, it does something else.
And to set up that test, you need relational operators, like less than, greater than, or equal to.
Right. Let's use the check valve example from our source material. An engineer needs to know if a valve is open or closed based on a pressure sensor. The rule is simple. If the pressure is 20 psi or more, the valve is open.
So how would you write that IF function?
It would be something like IF A3 20, open, closed. So it checks if the value in cell A3 is greater than or equal to 20. If it is, it prints open. If not, it prints closed.
And the real advantage there is the speed. If you have a log file with 10,000 pressure readings, you don't check them one by one.
No, you copy that one formula down the whole column, and in seconds you have the operational status for every single point in time. It's automated decision-making.
So once we have all this data and these automated decisions, we need to communicate the results. That brings us to plotting engineering data.
And the number one takeaway here for any kind of analytical work is that engineers almost exclusively use the XY scatter chart type.
Not the standard line chart. Why is that?
Because you want to see the relationship between 2 continuous numerical variables. A line chart is for categorized data, which is usually not what you're analyzing in an experiment.
And for a professional report, a chart can't just be a picture. It has to tell the whole story on its own.
100%. It needs clear axis labels with units, a descriptive title, a figure number, and if you have multiple data sets on there, you absolutely need a legend.
But what about the tricky situations? Like if you want to plot air temperature and wind speed on the same chart over time, their scales are completely different.
And if you try to put them on the same y-axis, the wind speed data will just look like a flat line at the bottom. It's unreadable.
So what's the solution?
You have to enable the secondary axis. You plot both data sets, then you format the wind speed series to use a secondary vertical axis. So you'll have temperature on the left y-axis and wind speed on the right y-axis. Now, both are presented accurately on one figure.
That is such an essential tip for clear communication. Okay, let's move to the real heavy lifting, matrix computation.
Matrices are just arrays of numbers. Engineers use them all the time to solve large systems of simultaneous linear equations, like in structural analysis.
And Excel has functions for this. I see ML-MIL-T for matrix multiplication and MINVERSE for, well, the inverse of a matrix.
It does, but using them requires a very specific trick. This might be the most important single procedure we talk about today.
The one thing you have to remember.
Yes. When you perform a matrix operation, you can't just type the formula and hit enter. It won't work.
What do you do instead?
First, you have to select the entire destination range. So if you're multiplying two 3x3 matrices, you have to select a 3x3 block of empty cells first.
Okay, I've selected the range, then I type the formula in the formula bar.
And then this is the secret handshake. You press Ctrl plus Shift plus Enter all at the same time.
Not just enter.
Not just Enter. That key combination tells Excel to execute it as an array formula across all the cells you selected. If you forget, it fails. It's the difference between solving the problem instantly and being completely stuck.
That is a secret weapon. Okay, last big topic. Let's talk about taking messy, real-world experimental data and turning it into a clean, predictive model using curve fitting.
Curve fitting is all about finding the mathematical equation, the trend line, that best describes your data points. A classic example is measuring load and deflection on a spring to find its spring constant.
So walk me through the procedure.
First, you plot your data points as an XY scatter chart. Just the points, no connecting lines. Then you right-click on any of those data points and select Add Trend Line.
And then you get a choice of what kind of fit to use, like linear or polynomial or something else.
Right. And once you've chosen your fit type, there are two checkboxes that are absolutely essential.
What are they?
You must check Display Equation on Chart. That's the actual engineering formula you're looking for. And display R-squared value on chart.
Ah, the R-squared value. The coefficient of determination. What is that actually telling me?
It's a score for how good the fit is. It ranges from 0 to 1. An R-squared of 1 is a perfect fit. Every single one of your data points lands exactly on the line.
And a value near 0 is a bad fit.
A terrible fit. It means there's no correlation, and that equation is basically useless for making predictions.
So if I'm doing a materials test, what kind of R-squared value am I hoping to see?
You really want to be above 0.95, ideally above 0.99. A high value like that gives you strong confidence that the physical law you've just derived from your experiment is robust and reliable.
This has been a really fascinating deep dive into this toolkit. We've gone from, the basics of organization with named ranges all the way to the critical rules for formulas and cell referencing for automation.
We also hit on the utility of functions like stdev for reliability, the if function for making decisions, and then these high-level applications like professional charting, the secret to matrix math, and turning raw data into predictive formulas.
And the relevance is just so clear. This is the platform for modeling physical laws and analyzing complex data without all the programming overhead you had decades ago.
So we'll leave you with this final thought. We focused mostly on math and stats functions today, but the source material also mentions that Excel has a whole suite of specialized financial functions, things like future value, present value, number of periods.
NPER, FV, PV.
Exactly. Now that you're armed with how to structure complex engineering formulas and use absolute references for constants, think about this. How could you combine those financial functions with your engineering models? How could you assess not just the physical performance, but the long-term economic viability of a machine or structural design, all within a single seamless workbook?